Hi everyone, my name is Aaron Clasky. I have with me Anthony Silvaroli, and together with Chris Ling and Josh Wicks, we make Pyroshield, Electrospun Polyimides Nanocomposite for fire protection. So just as a brief summary of our presentation, we're going to first look into some of the motivation, how we got to our design, and then we'll go over the fabrication, validation processes, our results, and then conclude with conclusions, challenges, and next steps. So the primary motivation we're looking at is heat stress. Firefighters face obviously very high heat conditions, and as you can see from the figure on the slide, this correlates directly to cardiovascular complications. And these complications actually account for about 50% of firefighter deaths annually. So this is pretty significant. From this, we decided to focus on the heat stress element as sort of like the root cause for this and alleviate it as much as possible. So our focus is on the turnout gear. The turnout gear is essentially the jacket, the PPE that firefighters wear, and it's made up of several different layers. The layer that we're planning on to focus on is the thermal barrier, which is circled on the slide here. And so the overall goal of this project is to engineer a material to withstand higher temperatures, to either replace or improve the thermal barrier that is there now. So some of the existing technology, the main one is Nomex by DuPont. This is a fire-resistant polymer fabric. A couple of the main advantages of this fabric, we have it chars instead of melting, and it doesn't catch fire. And it also has low thermal conductivity, so the heat dissipation through the fabric isn't very high. However, a couple of the shortcomings that we wanted to focus on, thermal stability in air is relatively low. We'll talk about this a little bit further on. And the resilience at high temperatures we think can be significantly improved. So from this, from our design, we came up with customer specifications. The primary one, the most important, is thermal stability. We want the thermal layer to be as stable as possible. Secondary is the thermal resistance. This has more to do with like the thermal conductivity. We don't want the heat to dissipate too easily through the fabric. And then some tertiary requirements. So we have up here, such as like affordability, lightweight, breathable, these sort of things that would make the overall product better. So primary are some benchmarks. Primary benchmark is to increase the thermal stability. This is basically encompassed by the thermal degradation temperature. We want this to be at or above 572 degrees Celsius. And the secondary one, excuse me, is to increase the glass transition temperature. This is the mechanical stability or integrity of the polymer or of the material. And we want this to be above 283 degrees Celsius. These two numbers come from existing polymeric solutions in literature, and so we wanted to at least match them or beat them. And then our tertiary one is to decrease thermal conductivity. This number is actually taken directly from the Nomex data sheet.
So our design, in order to improve this thermal barrier, is to create a novel nanomaterial with three main components. The first is a base polymer of the type called polyimide, which has high thermal resistance and temperature stability. And we plan to embed nanomaterials into this polymer in order to create a nanocomposite with superior properties. In order to process this material into something that we can incorporate into a textile, we planned to use a technique called electrospinning in order to create nano-sized fibers, kind of like the ones imaged up there. This is not ours, but this is an example of a polymer nanocomposite fiber that we would be able to use to make polyimide nanocomposite fibers for our thermal protection. So the reason we chose polyimide as our base polymer is because it has a very high thermal stability. It has excellent thermal degradation temperature and glass transition temperature for a polymer material. It also has the unique property of being able to self-extinguish itself by releasing compounds that prevent flames from propagating on the surface. This is commonly used a lot in research and in the industry for heat-resistant applications that require polymeric materials. As you can see here, this is the structure of the polyimide we are using for our project. So incorporating into this polymeric material, we're adding nanomaterials. These have been shown in a variety of literature sources to improve thermal stability, whether it's by acting as a protective barrier for the underlying polymer material, or by reducing the motion of the chains of the polymer. we chose to use a number of different nanomaterials and see which ones gave us the best improvement. And the ones that we chose were alumina, used for its very good thermal stability, clausite and attapelgite clay, because they can offer sacrificial properties for the composite, and graphene oxide, because we believe that these carbon network materials that we've seen in similar properties with CNTs, we could use similar properties to increase the thermal stability. And to process all of this, we chose electrospinning because it can form nano-sized fibers that can be lightweight and breathable as a porous fabric. And we also chose scalable. It's because it's a scalable method that can be used with a machine such as this on the slide here. In order to test and validate the things that we made, we chose a number of characterization techniques that we'll go into a little bit more detail later. And we also plan to do an extensive design of experiment so that we could optimize our final prototype to give the best properties.
So now we're going to go through a quick fabrication overview of how we made our polyimide from start to finish. So the first thing that we had to do was synthesize a precursor polymer. This polymer is called polyamic acid. And it's made up of pyromellitic dianhydride, PMDA, and 4,4-oxydianiline, ODA. And you see on the slide here, this is a simple polycondensation reaction that we ran in DMF. And then we characterized it using FTIR. And the formation of a peak right here, about 1550 to 1540 wave number, is characteristic of an amide bond. And so we took this as proof that we successfully made the PAA. Next thing we wanted to do was disperse the nanomaterials. In order to get the properties that we desire, we need to make sure these nanomaterials are well dispersed within the polymer matrix. And so for this reason, we did some dispersion studies. So we used a turbidimeter to measure the settling time, or the settling rates of different nanomaterials dispersed in DMF, which is the solvent that we're using. As you can see on the graph here, at 20-minute pulse sonication, the clausite, attapelgite, and alumina all showed very good stability. And so we weren't able to measure graphene oxide directly because it interfered with the turbidity measurement, but we figured it will follow the same trend as these materials, and so we used 20-minute sonication across the board.
So once we processed our precursor polymer and our nanomaterials, we then proceeded with electrospinning. In order to validate our electrospinning setup, we used polyethylene oxide and water to make sure that we can produce fibers with anything. So we used this material, and we were able to get very nice fibers from our electrospinning setup, as you can see here. This is an SEM image of PEO fibers that we made. And this kind of verified that we can use our electrospinning setup correctly. So after electrospinning our precursor nanocomposite, we then proceeded to our final step, which is imidizing the polymer. This is a temperature treatment where we raise the nanocomposite to 300 degrees Celsius in a tube furnace. And this kind of closes the ring that forms the polyimide here. So it converts our polyamic acid into polyimide. This sort of linkage is very important for the thermal properties. And as you can see here, especially from the existence of a peak at 1380, a wave number, we showed that the imide bond was formed from the CN stretching that is characteristic of imide.
So after completing some of these validation tests, we decided to electrospin our actual precursor polymer, polyamic acid. So you see in the SCM image here, this is what we got. This is sort of a more sparse area of the sample, but this is, we got microspheres instead of fibers. And so this is actually an artifact of electrospraying instead of electrospinning. The main difference being that the polymer stream that's formed with electrospinning, it breaks apart and instead forms droplets. And this is most likely due to the molecular weight of the polyamic acid that we made. We're hypothesizing that because we made it ourselves, the molecular weight wasn't long enough or wasn't large enough in order to keep make the stream cohesive. So we got microspheres instead. And then, so these are some more zoomed in pictures of the same sample. We noticed we got a dimpled morphology for pretty much all of the microspheres that we looked at. And then we also got some fibers like connecting the spheres together. So overall, this wasn't like the exact morphology that we were looking for, but we did end up getting good coverage and fairly good uniformity in terms of the size of the microspheres. And we know that we have successfully made our polymer, so we decided to move forward with the nanomaterials. So some of these images here, this is alumina, 3-weight percent, and closite, 28, 3-weight percent. One of the major takeaways from these images is there's no huge like aggregates of material. A lot of, like, you can see the spheres, and they have a fairly uniform morphology, but we don't have like pockets of nanomaterials and pockets of spheres. It's pretty well dispersed through. And then same thing with the tapelgite and graphene oxide. I'd like to point out the graphene oxide just because it's the most evident one. You can see there's like platelets around that are like interspersed along with the microspheres. This showed us that we got actually like really good dispersion with the graphene oxide, partly because we weren't able to test this directly with the turbidimeter. But yeah, so that's what we were looking for.
So to characterize our material, we used TGA, thermogravimetric analysis, to determine the degradation temperature of our composites. We took the temperature at 5% material loss and 50% material loss in order to get an idea for the onset temperature and what the temperature was at peak degradation. What we noticed is for at 5% degradation, there was some improvement when we added alumina nanoparticles to our polyimide when we compare it to just the plain polymer. But this effect is not particularly consistent when we look at all the other materials. It seems that some of the onset temperatures were pushed to actually a lower temperature with some of the nanomaterials. However, when we look at the 50% degradation temperature, which is kind of more indicative of when the peak degradation rate is occurring, we notice that we were able to improve the degradation temperature at that point by up to like 10 degrees Celsius, particularly for the alumina sample. This is definitely our best nanomaterial because it showed some improvement in both the 5% and 50% degradation.
So some of the main challenges that we faced when we were doing this project, probably the most significant one was actually producing the fibers using our own polymer. This ended up taking a lot longer than we anticipated. As we said, this is likely due to the low molecular weight of polyamic acid. It could also have to do with the purity of the actual sample. So when we were looking up the procedures in literature, the ones that made their own polyamic acid did not purify it. They took it directly and electrospun it. So we didn't feel the need to develop our own purification method. And as such, in hindsight, we hypothesized that the presence of like monomers and short chain oligomers may have also contributed to the formation of droplets as well. And then additionally, the sample yield from the aluminum substrate, because what we ended up, this is an example of one of our samples. What we ended up with was sort of like a coating. And so in order to run the characterization, especially for TGA, but also for DSC or any other characterization method, we need to have a non-negligible amount of material, obviously. And so we were able to get about 3 to 4 milligrams off for most of our TGA samples, which was good, but it was something that we really had to like look into later on in our project. So some of the big conclusions that we can draw from this project. Firstly, like we designed and we developed our own experimental synthesis procedure from start to finish to synthesize this high heat polymer, our high heat resistant polymer. We were able to improve the thermal degradation properties with nanomaterials, most specifically with alumina. This had the best effect at 5% and 50% thermal degradation. And so we would like to look into that further. And then finally, we also found that electrospinning method that we used like given the parameters that we had, did not produce the desired morphology. But it did give us good coverage with fairly uniform microspheres, and we were able to still characterize the thermal properties and get some good data.
So if we were to continue with this project and try to develop it further, there's a few things that we would want to improve upon. First of all, we would want to investigate using a pre-made precursor polymer. from a supplier such as Sigma Eldritch. Perhaps we would be able to get a larger molecular weight that way, and with the larger molecular weight, we might be able to form fibers with our electrospinning. The issue with that is even though we were able to obtain some of this supplier material, it was dissolved in a much less volatile solvent than what we were using. It was dissolved in NMP, which was not evaporating properly in our electrospinning setup, and therefore was not forming fibers. It was much worse than actually what we were using when we made our own. So we would have to find a way to get around this. Some ideas would have been to maybe use a co-solvent that would evaporate faster so that we'd be able to get better drying and so we could form cohesive fibers. Additionally, we would want to do a more in-depth characterization of our material and a design of experiments in order to determine the effects of all of the parameters in our setup and completely optimize our coating. We would want to make sure we can figure out things like the glass transition temperature, the thermal conductivity, and the mechanical integrity of our product if we had more time. So thank you for listening to our presentation. We'd just like to make the following acknowledgements to everyone who helped us, especially our advisor, Professor Leonardo Simon, helped us with getting us lab space and giving us advice and guidance. So thank you very much.